You're probably already pretty familiar with the idea about the intersection of two lines in two space. And sometimes when we think about that, we think about just the geometric possibilities. If you have two lines on the XY Cartesian plane, what might they look like? Well, one possibility is they look like this and they intersect in one place. Another possibility is that the two lines are parallel and don't actually intersect. And a third possibility that's a little bit strange, but technically is a possibility, is they could actually just be the same line, one line on top of each other. So we have those three different scenarios. Let's look at a question where we find the point of intersection between two lines. So here I have my two lines, and I've labeled them equation 1 and equation 2. There are two ways to solve this linear system. One way is using substitution, the other is elimination. Elimination is the method where you add or subtract the two equations together somehow in order to eliminate a variable. We're going to use the idea of elimination a lot in the coming lessons, but today's lesson focuses more on substitution. So let's actually look at substitution. I start with equation 1 and I solve for y because I notice that that is very easy to solve for. It doesn't introduce any fractions or anything like that. I then sub that new equation into equation 2 for y. We're then going to solve for x, and then once you get that answer, sub it back into the first equation to solve for y. Let's take a look at what the algebra looks like. There you see the rest of the algebra there. We expand with the 3, we solve for x, we then take that value of x and sub it into equation 1 and solve for y and get y equals 6. So we have one solution here, which corresponds to the point -1, 6. Now this is the algebraic part of the problem, as opposed to the geometric part. We're going to look a lot at comparing algebra and geometry this unit. In fact, the name of this topic could be linear algebra or algebra and geometry. So it's sometimes the case that we have two equations and two unknowns, two linear equations, and we just want to find the solution. We want to find the value of x and y that satisfies both equations, and that's what we've done here. The geometry of it tells us what to expect when we have two linear equations and two variables, that we might get one solution, as we did in that example below, that we might not get any solutions, or we might get an infinite number of solutions. So that's how the algebra and geometry compares. Let's start with the geometry of equations of lines in 3 space, and then let's see, well, what does that tell us about what kind of algebra to expect as well. So let's just take a minute, think about the possibilities for how two lines might intersect in 3 space. Well, some of the same possibilities as in 2 space exist. They could intersect in one place. They could still be parallel. We can have parallel lines in 3 space. Their direction vectors are collinear or the same. Technically, we could have the same line too. We could have that very strange case where the lines are exactly the same. But there is actually, that's 3 possibilities. There's a 4th possibility. Can you think about what it would be? The other possibility, if you think about two lines in 3 space, is they're not parallel and they don't intersect. So imagine one line just missing the other one. That's not too hard to understand why that could happen. Just in 3 space, they don't have to intersect if they're parallel. They can miss each other. I think of them like rockets zipping past each other or something like that, not intersecting. In this case, these are actually called skew lines and have no point of intersection either. Of course, it's very difficult to draw two skew lines on a page, but maybe you do something like this, leave a gap there. I don't know, whatever it takes for you to get that sort of 3D idea. Now, let's look at the intersection of two lines in 3 space, and we'll come back to this and see how does the algebra end up looking like. Notice that in some ways, although there's 4 cases instead of 3, we do have the same outcomes, either one solution, no solutions, or an infinite number of solutions that form a line, because the skew line still gives no solutions. Sort of similar to the parallel lines, but it's something when we do the algebra, we're going to find the geometry teaches us something we have to be careful about. You'll see what I mean as we get to it. Okay, so as an example, find the intersection of these lines that are both in 2 space, three space, and we have their vector equations. So what I've done to start off with right away is I have changed them to their parametric equations, which are quite a bit easier to deal with. Now, if we think back to the idea of substitution, if we have that x equals negative 1 plus 3t and x equals negative 1 plus 2s, well, we're looking to solve this, we want to know when are the x's the same. So we can combine that equation to get negative 1 plus 3t is equal to negative 1 plus 2s. We do the same thing for the two equations involving y. Y plus 1 plus 4t equals 3s. And finally for z as well, negative 2t is equal to negative 7 plus s. So you'll notice that we actually have three equations here. However, each equation has two unknowns. So we have three equations, two unknowns. So in some ways, we could actually go right back up to our geometry part here. We could look at the geometry part and say, this problem has been reduced to three linear equations with two variables. So let's look at solving that. The first thing I would do is I would take each of these equations and I would kind of combine terms, group stuff however I want. I tend to put my variables on the left and my constant on the right, but it's up to you. One simpler equation might be to say that negative 2s plus 3t is equal to 0. And I can do the same thing for the other two equations, and let's just take a look at what we get when we do that. And there you see the three equations we get with the s's and the t's on the left. Now, three equations, two unknowns. How do you solve that? Well, to start with, we are going to just work with two of the equations. So right now, I think I'm going to work with equations 2 and equation 3. So I'm basically going to solve these two equations here together first. Now, I told you that today's methods involve substitution more than elimination, and maybe that was a little bit misleading. We use substitution to kind of combine these two equations to get this system right here. But now when we're solving equations 2 and 3, we can use either substitution or elimination. It's fine. So what I'm going to do is I'm actually going to go and I'm going to rewrite equation 2 as negative 3s plus 4t is equal to negative 1. And then I'm going to do eliminations. I'm actually going to take equation 3 and I'm going to double it. So 2 times equation 3 will give me negative 2s minus 4t equals negative 14. And now what I can do is I can add those two equations together. And when I do that, we're going to eliminate the t's, solve for s, and go back and go from there. Let's just take a look at that. So I add those two equations together and I eliminate the t's. I get an answer of s equals 3. And then I plug that back into, this is now into equation 3 again I used here. Okay, and solve for t and got t equals 2. So I solved this system right here and got that s equals 3 and t equals 2. Now, hang on a second. I'm not quite done yet. And this is probably the trickiest part of the lesson to understand. And that's that s and t are happy in these two equations right here. Okay, if you sub in s equals 3, t equals 2, both equations are balanced. We did not use equation 1 at all, though. Equation 1 is like a new restriction. It demands that negative 2s plus 3t equals 0. Kind of a party pooper, isn't it? Because now our original answer of s equals 3 and t equals 2, it might not be happy in that equation. Well, let's find out if it is. So we call that checking an equation 1. If I do that, I will look and I will see, well, the right side is 0. That's pretty easy. The left side will become negative 2 times 3 plus 3 times 2, subbing my values of s and t in, and I get also that is 0 as well. So as it turns out, the check worked out, and s equals 3 and t equals 2 is our solution to all three equations. So we can kind of just confirm that in equation 1. Okay, if you want to think about that as being a good thing or bad, it doesn't really matter. Now, we still haven't actually solved the problem, because that's just our values of s and t. We actually are looking for three solutions here. X, y, and z coordinates are x, y, and z values. So we need to use our parameters to solve for x, y, and z. Now, keep in mind, since this is the point of intersection, the using s or t in either equation will give you the right answer. Sorry, if you put s equals 3 into this set of equations here, you're going to get x, y, and z. You'll get the same x, y, and z as you plug in t equals 2 into the 3 equations here. So why don't you go ahead and plug those two parameters, s and t, into either set of parametric equations and see what you get. I'll do the same thing, and you'll find out, be able to check your answer that way. So I chose to use the second equation. That's the equation with s as the parameter. And I subbed s equals 3 into the 3 parametric equations and got x equals 5, y equals 9, and z equals -4 for our coordinates of our point of intersection. Five, 9, -4. Let's try another example. So in this example, we still want to work with parametric equations. However, one difference is, notice the second line is in a different form. It's in a symmetric equation. So we need to think about what the parametric equation is just a little bit more. So in this case, we could say that x is equal to 3 plus 2, I'll use s again for my parameter. Y is equal to 3s, and z would just be equal to z would be equal to s take away 1. So imagine that being over 1. The denominators, of course, give you your direction vector, which is your coefficient on the parameter, and then the opposite values give you the points here. Okay, so we're going to do the same thing now. Once we've got those parametric equations, we're going to combine them into 3 different equations by setting the right side of the corresponding equation equal to each other. So let's just do that next. So once I've combined them, I just quickly rearrange them. I kind of like seeing them with the s and the t's lined up here. So I've got 3 equations, 2 unknowns. Just like in the other example, I'm going to pick 2 equations to work with and kind of ignore the third one for now. I'll go with 2 and 3 again. I notice really easily that if I take equation 2 and I add it to equation 3, I'll eliminate the t's by doing that, and I'll get that -4s is equal to -2, which gives me that s is equal to 1/2. You might be wondering, why is it okay to add equations together in the first place? Well, the answer is, think about just looking at equation 2 here. And imagine you wanted to say add -1 to both sides of the equation. Well, you can do that. In fact, that's what we did. We added -1 to the right side of equation 2 to get -2. And we added -1 to the left side of the equation, but instead of adding -1, we added -s plus t, which makes sense because -s plus t is equal to -1. And that's why elimination works. So we got s is equal to 1/2. We're going to now sub that into either equation 2 or equation 3, probably equation 3. And we'll solve for t and see what we get. So to keep equation 2 and 3 happy, we need s is equal to 1/2 and t is equal to -1/2. Well, how about equation 1? We never bothered to check with it, so we need to do that next. If we do that, we sub in, we get obviously the right side is going to be equal to 1. The left side is going to be -2 times 1/2 plus 1/2, which is equal to -1 plus 1/2, which is equal to -1/2. So in this case, it's not balanced. S and t, there's no solution for all 3 equations. Only the second and third, and maybe the first and the third, but all 3 equations aren't happy at the same time. They're not all balanced, which means there is no solution to this example, or no point of intersection between these 2 lines. Now, are these lines parallel? Let's just take a look. No, they're not, because if you look, the first direction vector is equal to 1, -1, 1. The second direction vector is 2, 3, 1. I get that from the denominator again. And those aren't collinear. So these lines don't have the same direction, yet they do not intersect. So it must be the case that they are, in fact, skew lines. Didn't do a very good job drawing that, but I think you understand what I mean here. Something like that right there. They don't cross. So there's two cases. There are other possibilities, of course, for three-dimensional lines. They might not intersect at all because they're parallel. Well, hopefully we would see that if we looked at their direction vectors. And they also won't, they will intersect, sorry, at an infinite number of points if they happen to be the same line. And hopefully you would be able to figure that out as well. I'm going to leave those for you to try on your own. An interesting thing, don't worry too much about this if it confuses you, but notice that we realized that finding the point of intersection in 3 space was the same as solving 3 linear equations with 2 variables. Well, what's interesting about that is 3 equations and 2 variables could actually represent 3 equations of lines in 2 space. So it's actually the same possibilities here as finding the intersection of 3 lines in 2 space, which might intersect all at the same spot, which might all be parallel, or might intersect in 3 different locations. So I don't know, it's just kind of out there for you to think about. If you don't get that, then don't worry too much about it right now. Just thought I'd mention it. I do have one other example to show you, and that's finding the y-intercept of a line. Now, that's kind of like finding the intersection of 2 lines in 3 space, because the y-axis itself is in fact a line, and we want to figure out where this line crosses the y-axis. So again, we're going to start with the parametric equations. X equals 2 plus t, y equals 1 minus t, and z equals negative 1 plus t. Now, what is true about a y-intercept? Well, the x value and the z value have to both be 0. If the x value is anything but 0, then imagine it would like push this, it wouldn't be on the y-axis anymore. And if the z-axis was anything but 0, then that would raise it up here and it wouldn't cross the y-axis. So we know at the y-intercept, x equals 0 and z equals 0. Let's start with the idea of x being 0. We get 0 equals 2 plus t. T must be negative 2 in order for x to be 0. Well, if we set z equal to 0, we get 0 equals negative 1 plus t. T equals 1. So in order for z to be 0, t has to be equal to 1. But in order for x to be 0, t has to be equal to negative 2. Well, t can only have one value at one time, so this means that this never happens. There actually is no y-intercept. It's like the line and the y-axis are skew. They don't intersect at all. Okay, I've given you some questions to try, just focusing on the basics.